This is part two of the topic of random variables. Uh, in the last video, I explained the random numbers, so now we're going to talk about random variables. They have a probabilistic behavior. We need to find this behavior in order to not only simulate the process, but in order to really improve it. There are two kinds, discrete and continuous. I'm not going to stop to explain the discrete distribution and the continuous distribution, but Poisson is an example of a discrete distribution, exponential, uniform, and normal distributions are continuous distributions. We're going to see only one test to find out what kind of probabilistic distribution a set of data has, and this data it's now going to be a variable. So what we need to do first is graphic this data and establish a hypothesis. Uh, Looking at the graphic, at the histogram, what does it look like? Then we need to establish a table of frequencies. And first of all, we are going to subdivide the whole set of data in m subintervals, where m is the square root of n being the total quantity of numbers, or the total number of data that we have. We need to then define a frequency distribution table for the observed and the desired frequency. We have an observed frequency that it's the one that the data presents itself, and we have a desired frequency that is the frequency according to the distribution established in the hypothesis. The next thing we need to do is find out the quadratic chi value just by following this formula that you are seeing right now. And we are going to compare this value with a table value. This quadratic chi value is in terms of alpha and m minus 1. We need to remember that m is the number of intervals that we calculated on the step number 2, and it's the quadratic chi test. And in step number 5 says that if this quadratic chi value is lesser than the table value, then the data behaves as the statistical distribution defined in your hypothesis. The hypothesis could be any distribution that we know. So let's begin with an example. We have this set of data. This is there are 1, 2, 3, 4, 5 rows, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. So we have 50 numbers here, 50 random variables that we need to know where they come from or what kind of probabilistic behavior they have. First, we find some deterministic statistics like the average and the variance of this set of variables or this set of data. We establish an observed frequency distribution table. First of all, we calculate m, the number of intervals, by calculate the square root of n being 50. We have 7.07 that can be 7 intervals or 8 intervals. We can decide between those values, and there isn't a big error if we choose 7 or we choose 8 intervals. The maximum value of this set of data is 24 and the minimum is 7. Then the longitude of the interval is calculated by 24 minus 7, divided in 7, that are the number of intervals that we choose, and the longitude of the interval is 2.43. So we just take the minimum value and we add the longitude of the interval, and we keep doing that, and we have the lower level and upper level for each interval. Then we observe the data and we have the observed frequency. Between the values of 10 and 9.43, we have three numbers. Between 9.43 and 11.86, there are four numbers. Between 11.86 and 14.25, we have 15, and we can keep doing this until we get to the last interval from 21.58 to 24.01, and there are two observed values in there. Then we graphic this information of the table, and we have this histogram. We see the picture, and we ask ourselves what kind of distribution is. Is it discrete? Is it continuous? What is the distribution does it resembles? What does it look like? We establish a hypothesis. In this case, we are going to establish that the set of data of the variable represents a Poisson distribution, and we are going to find out if this is a correct hypothesis. First of all, we need to calculate the probability of being in each interval, because remember, the first step was calculating the observed frequency. We need to establish the estimated or the desired frequency for each interval if this distribution were a Poisson distribution. So we need the Poisson density distribution, or the formula for in this case, and in this specific case, we just put there the average, and we have this formula. As Poisson is a discrete distribution, we don't have probability in all the interval. It's not continuous, so there isn't any values between 7 and 8 or 7 and 9. So we're just interested in the values of 7, 8, and 9, the integer values in the interval, because it's a discrete distribution. So substituting in the formula, we have a probability of 0.0622. For the rest, those are the estimated probabilities. This is just a probability. We are searching for the desired frequency. We need to multiplicate this probability by the total number of data. If we have 50 values and there is a probability that these values of 0.0622, that these values are between 7 and 9.43, how many of these 50 numbers are going to be in this interval? We have to multiplicate this 0.0622 times 50. Doing this, we have this estimated frequency. So in the first interval, we have a desired frequency of 3.11, in the second interval of 5.745, in the third of 14.045, and there are the calculations for the rest of the intervals. Continuing with the method, we have an observed frequency, an estimated or a desired frequency, and now we calculate the C value, or the quadratic Chi value, by doing or applying this formula that we see over here. And the calculation of the c-value is 1.114. Finding the critical value of quadratic chi for an alpha error of 0.05 and m minus 1 intervals, we have a tables value of 12.592, and as the calculated quadratic chi value is less than the table value, we can safely say that the data follows a Poisson distribution. So what we are looking for here is that this value, this C, is less than the value that we calculated or that we observed in the table, in the critical value. So this is how the quadratic Chi test operates for any kind of distribution, being this the example for a Poisson distribution. Now you're going to perform this activity, this individual activity, and you're going to find whether the same data set can be considered as a normal distribution, as an exponential distribution, and as a uniform distribution. We already established that they are Poisson distribution, but what I want you to do is find out if they can be a normal, an exponential, or a uniform distribution. You're going to program this in Excel, and your solution is going to look kind of like this. This is the data. Here we can see the data, the frequency table, and there are my calculations for the exponential, the normal, and the uniform cases. And those are the responses, but I'm going to stop here this video so you can go and do this individual